The next learning objective is that I can mathematically relate the position of an object and its gravitational potential energy. This is about something called potential energy. We should stop and just understand, what does that mean? Potential energy is the energy an object has because of its position relative to other objects. For this one, when we're talking about gravitational potential energy, it's about how much energy an object has because of its distance away from an object that is gravitationally attracting it. Most of the time in classical mechanics on Earth, what we're talking about is how high up something is. Because we understand that if we drop an object from a large height above the ground, it's going to have a lot of energy, kinetic energy, when it reaches the ground. It's going to have more kinetic energy when it reaches the ground if it was dropped from a higher height, because it's going to get more speed. So this is basically determining how much energy an object has because of how far away it is from the ground. Now we're going to be doing from the ground near Earth's sea level. In a future learning objective, we're going to be applying gravitational potential energy, or the force of gravitation, on a scale of solar systems and planets. But for right now, we're going to be keeping it to close to Earth's surface, where we're going to have some approximations, and that's key. The formula that I'm about to teach you does not work for everything. It only works for when you are close to Earth's surface, specifically sea level. So this would even change if you were on the top of Mount Everest. Now, change in potential energy is defined as the force times the distance that force is applied, or distance that the object travels while that force is being applied. This is also not quite the whole truth. AP physics would go into exactly what this is. This is the definition of work, it's called. But for our class, this is what we're going to work with. So if we just replace the force with the definition of the force of gravity at Earth's surface, mg, that we're familiar with, then the change in potential energy an object undergoes is equal to the mass times the gravitational acceleration constant times the distance. Now, we're mostly talking about vertical distance, so we often change d to h, meaning height, of course. So what you get is that the change in potential energy, in this case specifically gravitational potential energy, is equal to the mass times the gravitational acceleration constant, that's that 9.8 value, times the change in height. Or we'll often write it more like this. We'll break the change in potential energy as the final minus the initial. And we're going to have that equal, well, these two don't change, final and initial. The mass of an object most likely is not going to change, or at least for our assumptions, we're going to assume the mass of an object is not changing. And the gravitational acceleration constant, again, we're assuming it's near Earth's surface, so we're also going to assume that doesn't change. That does change if we are really high up. So if you drop something from low Earth orbit, this value is not going to remain constant. That's where we need that more advanced definition of the force of gravity that we're going to learn in a future unit. And we're going to be multiplying that by the final height minus the initial height. Now, if we let the final gravitational potential energy equal 0 when the final height is 0, then what we'll get left with, because the final will cancel, the final here will cancel, and we have a negative and a negative that will cancel each other. What we get is that the initial gravitational potential energy, or we'll just say the gravitational potential energy then, is equal to the mass of an object times 9.8 meters per second squared times the height at which the object is dropped. Now, this situation, this assumption right here that we're saying that the final gravitational potential energy is equal to 0 when the final height is equal to 0, is what makes the most sense most times, because what we're talking about is an object is being dropped and hits the ground. And we're saying the ground is at height 0. And would an object have any gravitational potential energy if it's on the ground, if it's sitting on the ground? No, it doesn't make sense. It can't go any lower. Now, of course, if that ground dropped away from itself, like a hole just appeared, then yes, it would. But we could just redeclare that this bottom of the pit is a final height and make this assumption again, essentially. Let's apply this to an example. How much energy would a 100 kilogram weight have if it was 10 meters above the ground. So just how much energy does this system have, where we have a 100 kilogram object and it's 10 meters above the ground? All we got to do is apply the equation for the gravitational potential energy, which is mgh. We take 100 kilograms times 9.8 meters per second squared times 10 meters. And the number is going to turn out to be 9,800. But more importantly, take a look at the units. We have kilograms times meters per second squared. That's a mass times an acceleration times another meter. So we have this Newton times meter, which, if you remember from the previous lesson, a Newton times a meter is a unit of energy, but we're going to rewrite this as joules. So it turns out that this object has 9,800 joules of energy. Now, sometimes these joule numbers can get really large. So it's often useful to write them as kilojoules instead of just joules. So we divide by a factor of 1,000 and we get 9.8 kilojoules. So that is how you use the equation for the gravitational potential energy. And of course, if we needed to solve for what the original height was, assuming it has a certain amount of energy, it would just be a matter of rearranging algebraically this equation right here.